Okay, this is the last set of videos, which will sound a little bit better if I get my little microphone over here. There we go. Okay, and so when we talked about momentum in translation, all right, we talked about having a single object and then there was an impulse acting on that object. Okay, it could speed it up, it could slow it down, that sort of thing. And then we talked about what happens if we've got two objects that are interacting with each other. Okay, so we had sticky collisions and we had explosions, explosive collisions, and then we had elastic collisions. Well, with angular momentum, we have all of those things also. Okay, and so what we're going to be looking at in the first two videos here are some sticky collisions. Okay, where two objects come together. So then they have one final velocity in the end. But instead of a translational velocity, it's a rotational velocity. So in this case here, we've got a record player, and we're going to drop a record straight down onto that thing. Okay. Now in the problem there, they give you the specs for the mass of the turntable, radius of gyration for the turntable, and that sort of thing. And to start off with, the turntable is already spinning. Okay, and so what's going to happen is this thing down here is already spinning. This is going to drop on top of it. Okay, and so we're assuming that it's freely spinning, which isn't how an actual turntable would work. A turntable would keep spinning at 2 radians per second, but this one we're going to allow to sort of slow down if it wants to. Okay, so we're going to set this collision up, and exactly like we did when we were dealing with translational collisions, especially sticky collisions, get rid of that. With sticky collisions, we always said, well, we've got some P final, has to be some P initial, or something like that. P initials, P final, something. Okay. Well, we've got the same thing, okay, but we're going to be say that our initial angular momentum has to be equal to our final angular momentum. Okay, so initially I've got two objects. We're going to have here the moment of inertia for the record, whatever its angular velocity happens to be, plus the moment of inertia for the turntable, its velocity. And then we're going to have some combined moment of inertia, IR plus IT, and that's going to go onto some combined velocity term like that. Okay. Now, in our particular problem here, the record actually has no angular velocity to begin with. Okay, so we're going to toss that term, and then we're going to do a little bit of algebra here to figure out what's the final angular velocity, and we're going to say it's the initial there onto IT over IT plus IR. Okay. Now, we're used to seeing results like that when we're doing linear stuff. Okay. A lot of times we would see something like V final is V initial, and they would have like M1 over M1 plus M2. Okay. So we would get results like that all the time. So what I want to show you here is that algebraically, this is exactly the same thing. So we've got one object that has no velocity, all right, and then the other object that does. When we combine them, that's the result that we get. Okay. Now, when you do the calculation, okay, using the numbers that I had, that combined velocity is 1.908 radians per second. Okay. So let's kind of go over this from the top again. All right. So each object has momentum, but it's angular momentum this time. And all we're doing is we're going to combine them together. Okay, so that's our collision. This happens to be a sticky collision. All right. Now, these angular momentum problems can get pretty crazy, but we won't be getting crazy. We're going to keep it pretty easy, okay? But if you want to sort of imagine how crazy things might get, just imagine you take a little rubber ball, a little bouncy ball. Now, if you drop the ball straight down, it goes down and it comes back up. But let's suppose that right before you drop this ball, or as you're dropping the ball, you give it a spin, but it still drops straight down. Okay, now you know from experience it's not going to come straight back up. All right, it's going to come down and then it's going to boom, it's going to go off at the side like that. Okay, in sort of a crazy way. And in some sports, all right, that is you take advantage of that. Okay, for example, in tennis, okay, the way you might have a ball hit at different times, putting topspin on the ball or something like that. But in racquetball, I don't know if any of you have played racquetball before, but in racquetball, that's a critical skill to be able to get that ball to spin. Except in racquetball, you don't spin it with your racket. You spin it by the way you bounce off the walls and some things like that. So and it's kind of fun. I brought it up, so let me just draw a quick picture here. So if this is the racquetball court, okay, if you're over here, for example, and you hit the ball like this obliquely against the wall, it's going to spin a lot, and then it's going to bounce off here, and your opponent, everything in their brain is going to say, "Oh, that should be coming out this way," but it doesn't. He goes like pew across like that. It's amazing. It was a lot of fun. I used to play quite a bit of racquetball. Okay. Anyway, if we were going to work all that out and try to figure out, I drop this ball, it's spinning, where is it going to go? Then we would have to do that through the lens of angular momentum conservation. Okay. But most of our problems are going to be very straightforward. And so if you got your head around this one, then you really have the main idea.